In this lecture, I'm going to show you how to understand the physics of a discharging capacitor, where the capacitor is discharging through a resistor. This is often just referred to as the discharging cycle in an RC circuit. So RC just refers to the fact that we have a circuit that only has a resistor and a capacitor, right? So that's the RC circuit. So that in this particular example, there's actually not a battery, but you could imagine that the use of a battery at some point. So here's the idea. You start off at at some point in time earlier than when we're going to start a stopwatch, but what we've got is a capacitor that has already been charge separated. So you can see that the charge separation on the capacitor is called Q sub 0. So sub 0 is just to mark the initial charge separation across our capacitor, whose capacitance is value C, right? It doesn't matter whether or not it's got a dielectric or if this is parallel plate capacitor or some other configuration of conductors. It just matters that what its capacitance is. And the fact that it's already charge separated. That is, it's already got a voltage, but that voltage is stuck there. That charge is stuck there, right? Because it can't cross the empty gap, and it can't move through the space from one conductor to the other because it's surrounded by insulator materials. And then over here, off to the side, is a resistor with two wires attached top and bottom, and all we're going to do is move this resistor with its wires just over to here and make a connection, right? That's what we're going to do. So let me erase all that. So we're going to make contact, and we're going to mark that time as time equals to 0. And what's going to happen is, because I have a lot of charge separated on this capacitor, the voltage across that capacitor is actually fairly large, right? So if the voltage is really big, then that voltage can cause a large current to flow through this resistor, right? It leads to a big current in the circuit, which empties the capacitor quickly, right? It's emptying the capacitor quickly. But if you empty the capacitor so that it's got less charge separated, then the voltage across that capacitor will be smaller. And if it's smaller, then it cannot push as fast of a current through this resistor, so the current slows down and the capacitor is emptying slower, right? It empties slower. And this just keeps going, and at some point, I finally gets to 0, and we have finished discharging the capacitor. So there isn't going to be any charge separation anymore. There's no more voltage, so there's no more current that's continuing to take charge away from the upper plate and put it on the lower plate. And I'm talking in terms of a conventional current. Okay, so this is what's going to happen, right? But in a sense, this process, right? This is a process. It develops in time. It's dynamical. That's what physicists say when something develops in time. We'll say that the current goes to 0, the charge separation goes to 0 in the long time limit that we wait an infinite amount of time, right? Which is not a practical thing to do. RC circuits, the charge will diminish on the capacitor, but you'll remember that that the smallest unit of charge to move on in a circuit is really an electron. So it's not an infinite time in a real sense. But in my mathematical model, you have to wait an infinite amount of time before the capacitor is fully discharged. Okay, so how do we solve this? Like, how do we get the dynamics? right? So how do we get the dynamics? What is the physics, right? We need something that's kind of like an F equals ma, right? But this isn't going to work for us because, yeah, it's just not the right avenue. So it turns out that Kirchhoff's loop rule is going to be our physics. It's going to give us the physics. So what's the loop rule look like? Well, let's do this. So here is the capacitor. Here is the resistor. And I'm going to put them together in a circuit. So I've already moved the resistor over and made conductive contact with the leads of the capacitor. And this is what I have. And this thing actually has a charge separated that is a function of time. And there is a current in the circuit that is a function of time, right? We just did some basic physics, right? Some conceptual thinking and said, well, we'll have a large current at the beginning and a smaller current later. And as the capacitor empties, that must mean that the charge on the capacitor, right, the charge separation is also diminishing. It's getting smaller and smaller. So these are time-dependent quantities, right? So let's pick a direction and write down Kirchhoff's loop rule. So if you look, right, the sum of the drops adds up to 0. But as I move along, right, so here's my pointer. As I move along the loop, the first thing I encounter is the capacitor. And the way that I go across the capacitor is from low to high, right? Low to high, just like in a battery. So this is considered a gain, which is a negative drop. So I'm going to put it in with a minus sign. So this is negative, the voltage across a capacitor. But the voltage across a capacitor in terms of the charge is the charge separated across the capacitor divided by the capacitance. So this is the drop across the capacitor in this direction, which secretly is a gain. That's why I put the minus sign. But then the assumed current flow, which is actually a good choice, is down through the resistor, right? The conventional current is the motion of positive charge flow, and positive charges are going to leave this positively charged plate, right? All that positive charge is repelling each other. They don't actually want to be that close to each other. They'd rather be close to this negative charge, but the only way to get there is through the conductive direction, not across the non-conductive or insulated direction. So you just flow through the resistor. So you flow with, or the Kirchhoff loop is going across the resistor in the direction of the current. So that's actually a drop. So it comes with a plus sign, and it's just I of t times R. And this right here is my physics. It's the relationship between the current and the charge separation, and it was given to me by Kirchhoff's loop rule. Kirchhoff's loop rule in general can always be used. It's an amazing tool, right? None of the equivalent capacitance and resistor rules would help you here because you don't have an equivalent capacitance or resistance when you have a mixture of capacitors and resistors, right? They don't mix the way that you learned earlier. Okay, so here's my physics. But there's another thing. So Q and I are related, but they're not related algebraically. They're actually related in a calculus sense, right? Right, you get current only because the charge is changing in time. You get current because the charge separation on the capacitor is changing. But this is really important in this discharging case, right? We're watching the capacitor lose the charge separation. So Q of t is getting smaller and smaller, closer to 0. negative q of t is actually growing up to 0 because it's a negative number, right? But anyways, so I is because of dq by dt, but I is positive when dq by dt is negative. That is, when the charge on the capacitor is decreasing, we have a positive current. So the relationship has this surprising negative sign, right? So I'll put a big exclamation point. You've seen earlier that we just said that the current was the rate that charge moves past a point. And that is still true. But in this case, when I relate, right, when I'm doing some physics, I have to remember actually that if the capacitor loses charge, I get a positive current. So dq by dt itself is negative, so I have to tack on an extra negative sign to make negative times negative be positive, so I is positive, is the idea. All right, so once I have this, I can go up and actually use this relationship in the Kirchhoff loop rule. So I'm going to do one step of Kirchhoff loop rule algebra. I'm going to move q of t divided by c over to the left-hand side. Right? Up here, there was a minus sign because of a gain, not a drop. And then it's equal to I of t times r. Like this. And now I'm going to put in the relationship. I'm going to replace I with negative dq by dt. So I'm going to drop the time dependence for it. No, I'm not. I'm going to leave it in. So q of t, right, divided by c equals 2. And then I of t is negative, right? So it's negative r times di by dt, where I is a function of time. So what can we do with this? Oops, sorry. This is actually, I of t is replaced by dq by dt. Excuse me, like that. Okay, so, right, this was this argument I just made. All right, so I've got this thing. So what I'm going to do is I'm going to separate variables. So this may be something you learned in math. I hope you did in calculus, excuse me. So I'm going to put all of the time dependence on one side, including this little dt. That's an amount of time. It's infinitesimal. But in algebraic sense, I can move it over to the left side. So I've got dt over here. I'm going to move the negative r also underneath. So I've got negative and then dt over rc, and it's equal to, so the dq is on the right hand side, I'm going to move q of t underneath, like that. So q right here is a function of time, but I can imagine it just taking the value charge, and it's divided underneath small increments of diminishing charge. And that's, the charge is diminishing while the time advances into the future. That's why there's this relative minus sign. And I've got this thing called r times c, which you'll see its importance in just a second. But what this is set up for us to do is something really interesting. It's actually set up for us to do an integral. So before I add the integral signs, the truth is this is actually true in the sense of changes. So if I know what the charge separation is, and I know that the charge separation is going to diminish by an amount dq, then dq over capital Q is equal to the amount of time I wait divided by r times c, but only if you agree that dq and dt are infinitesimally small, right? That's the calculus agreement. So what I'm going to do, though, is this is already true. So if I integrate with the appropriate bounds, then it's also true after the integration. but the bounds have to match. And the way I'm going to match them is I'm going to say that at time t equals to 0, the value of the charge, right? This is the charge separation, is q naught. And if I wait a certain amount of time, so this has to be promoted to a dummy variable or demoted, right? So I can do the integral. So if I wait that amount of time, then the charge is going to become q of t, right? The time-dependent charge. That's how I make the bounds agree. And so the left-hand side is really simple in terms of an integration, right? The integral of dt prime becomes t prime, and you evaluate it at t and 0 with a subtraction symbol, and it just becomes t over rc, but with a minus sign, right? The minus sign's out front. And this, though, the integral of dx over x is the natural log of x, right? So this is equal to the natural log, but you have to evaluate at the upper bound divided by the evaluation at the lower bound. So I get this thing right here. And if I want to solve for q of t in this algebra problem, right? So I've finished the calculus. It has now become an algebra problem. I want to know what is the charge as a function of time separated on the capacitor, and that's what q of t is. So the way you get out of a natural log is you take the exponential of both sides. So e to the minus t over rc is equal to, so it undoes the natural log. It's q of t over q sub 0, and this leads to so tau is the name of this Greek letter that looks like a T, Latin letter T, right? So it's the Greek letter tau, and it's reserved for what's referred to as the time constant of RC circuits. And it's just simply the resistance in the circuit times the capacitance in the circuit. All right. So if you were to draw this picture, right, if you had some value of Q naught, you could say that Q naught was equal to, I don't know, 5 microcoulombs. And that's just a starting point for a charge separated on a capacitor. We could say the capacitance was, I don't know, 10 nanofarads, and the resistance, let's put in, I don't know, 10 ohms or something like that, right? You can immediately get tau. It's the time constant. It'll be 100, right? It's R times C, but it's nanofarads ohms. And the thing is farads and ohms are SI units, and this SI unit combination is meant to be a time. So farad times ohm is just the second, but the nano doesn't go anywhere, so it stays there. It's the nanosecond, right? So tau is 100 nanoseconds. And the meaning of this, it looks like this. So you can see that the function is an exponential decay. It's a decay because I have a negative number up in the exponent, right? Yes, the argument of the exponent is negative. So if you look at q of t versus t, it starts at t equals to 0, right? That's the origin right here with the value q naught, and then it exponentially decays. My hand was shaking. It's hard to draw. Let's see. Like this. And asymptotically, you can see that the charge, as you wait longer and longer and longer, the charge gets smaller and smaller and smaller, but you have to go all the way out to t equals infinity, or t goes to infinity, to see q of t finally get to no charge, right? If you wanted, you can actually get the current. The current is negative dq by dt. Remember, that's how we started, or that was one of the steps in our process of getting this information. And it's just, I've got the function right here, right? And I can just take its derivative. So you get equals, so it'll be minus q naught, right? Actually, let me do it fully. So it'll be d by dt with a minus sign of q of t, which is q naught e to the minus t over tau. And if you take this derivative, can you see you're going to get a minus 1 over tau with the minus sign is going to be a positive 1 over tau, and then q naught, and then remember, taking the derivative of exponential, actually the exponential stays, it sticks around like this. So you get this, and you can remember that q naught, it's going to be q naught over r times c, e to the minus t over tau, because, tau is r times c. And if you look at the units of this thing, it will be in amps. If you think about it, the top is in coulombs and the bottom is in seconds, right? Because r times c is a time. And so charge per time is current. And this actually is the initial current. It's the current at time t equal to 0, right? So Q naught over RC is the initial blast of current right when you touch the resistor to the loaded capacitor, right? So at the very beginning, you get this initial blast of current, and the initial blast of current is Q naught over RC. All right. You can actually also get the voltage across the capacitor as a function of time, right? It's just the charge as a function of time divided by the capacitance, which is not time dependent, right? So there's lots of things you can get. Just to remind you, it all started with Kirchhoff's loop rule. Kirchhoff's loop rule gave us the physics